Electric propulsion could be the future of space travel. It offers unparalleled fuel efficiency compared to traditional chemical rockets. One of the most important devices on electric thrusters is a device called the Neutralizer. The exhaust from an electric thruster is made up of positive ions. The job of the neutralizer is to emit electrons, which go and mix with the positive ions in the exhaust to form an overall neutral charge. This is important to make sure that the spacecraft does not build a charge buildup. Hollow cathodes include an emitter, which is made up of a low work function material. Work function is the measure of how much energy it takes to remove an electron from an atom, so in this case, a lower work function is better. The emitter material is heated up, which then produces electrons, and these electrons go, and the ionized gas is fed in the cathode. This creates a plasma, and from this plasma, electrons can be extracted via the orifice and then used to neutralize the plume. One of the issues with hollow cathodes, especially here on Earth, is pollutants can go and poison the emitting material. Impurities from the gas being fed into it or from the surrounding environment can degrade the emitting material, leading to an increase in work function, which then requires an increase of heat to use the cathode, which eventually can lead to component failure. Undergraduate researchers at the Purdue Electrical Propulsion and Plasma Lab are working on a new type of neutralizer called the ICP neutralizer. ICP stands for Inductively Coupled Plasma, and it uses AC power that goes through an inductive coil to create an oscillating magnetic field, which then induces an electric field that accelerates electrons to ionize the gas in the discharge chamber. A more detailed video about ICP will be released in the near future, but it's important to recognize that the ICP doesn't have an emitter that can be poisoned like a traditional hollow cathode. I got to spend the day with David and Steven, who are working on testing this exciting new technology. Check it out.
Okay, it is currently 1:17 p.m. and David and Steven are wrapping up their setup and getting a chamber ready for pump down. Okay, Steven, can you please tell us what we're going to do today?
Yeah, so pretty much we're going to be testing our impedance matching network for our ICP neutralizer, and essentially this network is going to help us increase our power deposition. So we're trying to see how much this will actually increase our power deposition by today. And we're going to be testing 4 different frequencies that is going to, the range being 23 to 26 megahertz. In our whole setup, we have 3 different inputs. We have our signal generator, which we're going to set to from 23 to 26. It's at 23 right now. This signal generator is connected to our signal amplifier, which is going to amplify our signal to have about 250 watts of power. And this is going to go all the way through this cable, coaxial cable, and connect to our impedance directly to our impedance matching network, which then connects to our chamber that connects to our neutralizer, which currently isn't set up yet. But we're gonna use this oscilloscope to read the forward and reflected power, and then convert that to watts, and then we're gonna take the net sum or net difference between the forward and reflected power. That's going to give us our power deposition, and that's how we're going to characterize the performance of our neutralizer.
Right here we have our ICP neutralizer. So this coil is our most important component. We send alternating current electricity through it, and this is basically what allows us to create the plasma inside. This glass tube is known as our discharge chamber. It just contains the plasma volume and allows the plasma to be sustained. Over here on the inside, if you can see, we have this copper insert. This allows us to streamline the efficiency and get more performance out of this neutralizer for the same amount of gas. And this back plate component, this is just grounded to allow us to get more electrons from each amount of propellant.
Okay, it is 2:12 p.m. and David has told me that the chamber is pumped down and they're about to begin testing.
We have really strong results right now,
we're getting
which is unexpected.
Really good. Sparking.
Okay.
Hope record that, yeah. That is bright. Okay.
This is going to be very interesting data visualization.
Oh yeah.
Unplugged, right?
Yes, unplugged.
Two.
I'm predicting we're gonna get a new best today.
I mean, that's the idea, hopefully.
Yeah.
315. We're losing 15-20 watts already though through losses, so
yeah,
we'll see how it goes. 315. Right.
I mean, yeah, but we're at 23.
Yeah. You can plug it in.
Plugged in. Spark. Tell me when to spark.
You're good to spark.
I think we should try to like, I think we might want to like resolder some stuff. If we hear like any more like sparking from this. Yeah, there's sparking.
Yeah.
We should, I think we should resolder.
Okay, it is 2:27 p.m. And we had some tests going, but Steven noticed there might have been some sparks on the capacitor. So right now, David is resoldering it to try to get a better connection.
Yeah.
So Steven is now comparing the past data with the new data that they've collected so far.
Yeah, as I can, from what I'm seeing right now, we are getting plasma at a much lower amount of like turns. So at 23 before, we were getting much like I think our best result is probably like 332, 262, maybe. Yes, it might be that. Yeah, but like previously our best result at 23 was like we had plasma, but we didn't have very bright plasma at that. I think our best result was like 341, 281.
And what do the two different numbers mean?
That is the forward and reflected power. So right now we like barely just started testing, and we're already getting like some of the best results we've seen at 23 with the matching network swap. So this is gonna be promising, I think.
And so are we trying to minimize reflective power, right? Or
we're trying to maximize forward power and minimize reflective power. Yeah.
If it fails once more, I'm not gonna try to resolder again. I think it's just too damaged and we need to do a full replacement, which is gonna be a task for another day.
David, sorry, can you explain what the blue and the green are and what you're reading off of the oscilloscope?
Yeah, so right now we're collecting two different signals. We have one line, which is the blue. This collects our forward power, and the green, which is the reflected power, is what's rejected by the system. We're taking two sets of measurements right now. We're taking the power rejected by the system when there is no plasma. This is just our parasitic losses. And then we turn the plasma on, and we see the power rejected by the system in that state. When we compare those two power rejections, we can take out the parasitic losses and see just how much power is pumped specifically into the plasma, which is what we're trying to increase right now.
Nothing.
313, 291. Three 17 295. Fire at will.
Nothing.
319 296.
This.
Also, the sparker, you have a part that fell off.
Oh, this fell off. Oh. Didn't notice that. Okay.
Can you feel that inductor, the black one, if it's hot?
It's not hot.
Okay, because we had previously, it was coupling the power into that for some reason, which might be why we have such high losses. So I'm gonna try it one more time. Okay. 335 251. Okay.
Okay.
Fire at will.
Plasma.
Okay, it's really dim now.
Yeah.
333 247. And this does have plasma. Okay, this is the last state.
Some of our data might we might need to re-record some of the data then, because I didn't notice the thing was unplugged.
It's fine, I think.
Yeah, it honestly probably is.
Like when the plasma ignites, it ignites on its own.
Yeah.
Usually. Fire at will.
Plasma.
Okay. Yeah, it seems like we're definitely not going to go back and redo that.
Yeah,
312,
then we'll just redo that row
4.
like, next time. That is, wow.
I'm
that
going
is,
to deem that not safe to continue.
yeah, no, let's stop. Let's stop.
Okay.
No, we need to refabricate this.
Yeah.
Or you need to refabricate it.
So right now, the issue that we were experiencing is this connector over here. It needs to be electrically connected to both this side and this side. So what we did was we spliced two wires together and soldered them. The solder seems to have come off, so these two wires are not connected now. And what's happening is, since we're still sending electricity, there's a spark across the air gap, which is like burning up the wires and could lead to further failures. So for today, we're going to call this experiment here until we can fabricate a better connector.
Okay, David and Steven. So, I heard a lot of success in the beginning, and then we had some no plasmas, but can you summarize what were the results of the test and whether or not you felt it was successful?
Yeah, so overall, today's test, I want to say, was highly successful. We did have some drawbacks and some failures, which I'll get into in a second. But the first thing that we want to note is we had a strong improvement in our plasma performance. We got more power delivered and a stronger plasma in a region that we don't typically see it at. One thing that happened during the test is one of the connectors over here for our sparking device got dislodged. So there were a few calls of no plasma. That's because we were expecting plasma, but we weren't able to spark it. We caught this about halfway through, so that's going to be something to revisit at a future date. And our experiment was also unfortunately cut off early due to a second failure of our connector. This is because some of the wires got dislodged and there was arcing across an air gap, which is pretty bad and we don't want to see. So for safety reasons, we called the experiment off early. But in general, to summarize, we had a very strong success, a lot of hope for the future to revisit this and continue improving performance. And other than the failure, it was pretty much all success today.
Yeah, if we want to proceed with more experiments, if we want to proceed with this experiment in the future, we're going to have to refabricate the network, make the connections a lot more secure. And I mean, like David said, this is good data. This is the best plasma we've seen at 23 megahertz specifically. So I think that if we test this configuration at further frequencies with the better fabricated connectors, we will see probably the best plasma.
All right, thank you both for your time.
Thank you very much.
And there you have it, a day in the life of testing at the Purdue Electric Propulsion and Plasma Lab. It was awesome seeing David and Steven test this exciting new technology and seeing the beautiful plasma inside the vacuum chamber. The recent paper on ICP neutralizers can be found in the description, as well as a link to the Purdue EPPL website. Thanks for watching.